So let's start week 4. Just wait a minute. So in week 4, you would have studied about Morse circle first. You would have studied about Morse circle, right? And so the pen is now working. Wait a minute. I think there's some technical problem in my pen. Yeah. So apart from Morse circle, you would have also studied about some concepts of strain. Right? We'll adjust the camera a bit. Okay. So let me recapitulate quickly. So you would have studied about maximum principal stress and maximum shear stress. Right. So formula for uh, generalized, formula for normal stress was in terms of sigma xx and sigma yy into xy. So it was sigma xx plus sigma yy by 2 plus r cos 2 phi minus 12. Right. So this is the normal stress. This normal stress is on a plane which is making angle alpha with respect to x-axis in anti-clockwise direction. Okay, so this normal stress is on a plane with normal vector making an angle alpha with x-axis, right? Because this sigma xx is the normal stress on x plane and sigma y is normal stress on y plane. So obviously this is radius of the Mohr circle, r, capital R. So on a plane with normal vector making an angle alpha with x-axis in anti-clockwise direction. Right. Color has been used. So this is alpha and this phi was if you remember from the Mohr circle, what was this phi? So this phi was angle between the xy plane and the principal plane, right? So this was angle between um, yeah, xy plane normal also you can, I mean, xy plane and principal plane. So double of that appears in your Mohr circle. Okay. So similarly, the shear stress on a plane was given by r sine phi minus alpha. Right? So this was the shear stress, and the value of expression r was sigma xx minus sigma yy divided by 2 to the whole square plus 2xy to the whole square. So this was the expression for r, and we want to find out phi. So 10 to phi was equal to this twice of tau xy divided by sigma xx minus sigma y. This was the angle. Okay, so say phi is let me draw more circle or more stress plane. So this y-axis is corresponding to shear stress, and this x-axis is corresponding to normal stress, right? So now let's say you have three values of the principal stress. So lambda 1, lambda 2, lambda 3. Such that lambda 1 is greater than lambda 2 and lambda 2 is greater than lambda 3. So how will you mark it? So your lambda 1 will lie somewhere here. So it is the greatest. And lambda 2 will lie somewhere here. And lambda 3 will lie somewhere here, right? And if you draw circles passing through these points, this is the first circle. Let me choose different color. So let's say this is the first circle, right? And this is the second circle, right? And third circle will be outer one. So the third circle. So obviously the maximum value of shear stress also you can find corresponding to each Mohr circle. So here in the first case, maximum value of shear stress will be given by this point. And this point is nothing but, I mean, this height is nothing but the radius of this circle. The radius of the circle is nothing but lambda 1 minus lambda 2 by 2. Right? So this radius. So I can say that here the maximum shear stress is um, lambda 1 minus lambda 2 divided by 2. Right? And in this circle here, the maximum shear stress is this height here, which is the radius of this pink circle, which is lambda 2 minus lambda 3 by 2. So here you will get, and for the largest circle, whose green color. So the radius is given by this height here. Maybe center will lie somewhere. So radius will be given by this height. Okay. So this is obviously lambda 1 minus lambda 3 by 2. Okay. So this Mohr circle is corresponding to three-dimensional state of stress actually, because here you have three circles. So at a time you are taking, so to draw a particular Mohr circle, you need to have a set of planes which is whose normal is perpendicular to one of the principal directions, right? So in case of lambda 1, lambda 3 circle, you are taking a plane whose normal is perpendicular to second direction. Okay, let's say x, y, z are three directions. So its normal is perpendicular to y direction. When you are drawing lambda 2, lambda 3, you are taking set of planes whose normal is perpendicular to first direction, and when you are taking lambda 2, lambda 1, you are taking set of planes whose normal is perpendicular to third direction. And let's say you take any other plane, okay, um, whose normal may not be perpendicular to any of the principal directions. You take a generalized plane, okay, and you try to find out the normal stress and shear stress on that plane. So the value of the normal stress and shear stress on that plane will lie within this area, this yellow area which I'm highlighting. It's not going to lie in this area or this area. So any plane you take, any set of planes you take, the normal and shear stress on those planes are going to lie within this area only. It's not going to lie within these circles. It's going to lie outside of these circles, but inside this largest circle. And you can prove this also mathematically. Maybe you can try proving it. You just write a code on MATLAB. So in MATLAB, you can write a code and you can use some random number generators. So in MATLAB, you will get a lot of, you will get random number generator, means that random number generator will generate a lot of numbers for you. So those may be values corresponding to the normal stress and this shear stress, or just wait a minute. So you can use random number generators and then you can try to find out. So if you use random number generator, let me just think. So any other point on a principal plane or any other plane. So we have this formula, right, for normal stress and shear stress. So you start with any sigma xx and any sigma yy. And maybe if the plane is not. Okay, so I will maybe post this assignment or you can say this is not an assignment. You can just try at your home, and I'll just post this problem on the link of my YouTube channel. So this video will be uploaded on the YouTube channel, and you can go to that channel. And on the in the description of this video, you will get that problem statement. I'll specify that you have to use some random number generators, and you have to satisfy certain conditions. And you will see that if you will plot normal and shear stresses on different planes, okay, which need not to be perpendicular to one of the whose normal need not to be perpendicular to one of the principal planes. So you will see that set of those normal and shear stress for all the random number generators. So those points will lie in these regions. And if you will plot all those points, you will get a circle like this. There will be no point inside these circles. Obviously, you will have to fix this lambda 1, lambda 2, lambda 3. So lambda 1, lambda 2, lambda 3 will be known to you, right? So, and what will, I mean, the orientation of plane will be random, actually. Orientation of plane in 3 dimension will be random. So corresponding to fixed value of lambda 1, lambda 2, lambda 3 and random orientation of plane, you will get different normal stress and shear stress on that plane. And those normal stress and shear stress will lie in this region. And without writing MATLAB code also, you can just derive mathematically. There are in many books it has been done, so you can see that. So let me just, so I can just write here that the note that sigma comma tau for arbitrary planes occupy the shaded region. Okay. So there can be special cases also. So first special case one. So if lambda 1 is greater than lambda 2 and that is equal to lambda 3, it means two of the principal stresses are same. Okay. If two principal stresses are same, you will get only one more circle instead of three set of circles. So here your lambda 1 is there and your lambda 2 is smaller than lambda 1 and that is equal to lambda 3. So lambda 2 comma lambda 3 will lie here. So your circle will look like this. So obviously this is normal stress, this is stress. And for let's say you have all the principal values equal, lambda 2 is equal to lambda 3, lambda 1 is equal to lambda 2 is equal to lambda 3, so you'll get a point. This is sigma, this is tau. So all the principal stresses are same, so you'll get a point. Point means, so that is set of circle, you're getting a point, right? So what is the significance of this point? You would have also studied in the lectures. So let me recapitulate. Significant of this point is all your directions now are principal directions, right? Because you are only on the x-axis, I mean the normal stress axis. So all the directions, whether you go in any direction, all the directions are principal stress directions. And there is no shear stress present. This state of stress is known as hydrostatic state of stress. This happens when, let's say you have a body immersed in a fluid and let's say the dimensions of the body is very small compared to the depth of the depth at which it has been immersed. So the pressure acting on the body will be uniform from all the sides. So, and that will be normal stress, and that body will then be instead of hydrostatic state of stress, and all the planes will experience the same normal stress. Okay. So okay. Next, you would have also learned about stress invariants. So what are stress invariants? So stress invariants are, how do you get them? Firstly, you would have seen the derivation in the class. So there are three types of stress invariants. So these invariants do not change when you rotate your coordinate system, right? Invariant itself signifies that it is not going to vary. It's not going to vary when you rotate your coordinate system. So first invariant is denoted as I1, which is sum of all the principal stresses. And it actually it is the sum of diagonal elements, not the principal stresses, but since it is not going to vary. So if you now write in terms of principal stresses, then this sum is going to be same for all other planes as well. So you can also write it as trace of sigma. Trace means you have to sum the diagonal elements of stress matrix. Second invariant is, in terms of principal stresses, it's very easy to write second invariant. So it is nothing but lambda 1, lambda 2 plus lambda 2, lambda 3 plus lambda 3, lambda 1. Right? And if you write in terms of any other state of stress, I mean, on any other plane instead of principal planes, so you will get sigma 2 to sigma 3 3 plus sigma 1 1 sigma 3 3 plus sigma 1 1 sigma 2 2 minus sigma 1 2 square sigma 1 3 square minus sigma 2 3 square. Okay, we get this. So these are lambda 1, lambda 2, lambda 3 and principal stresses. Sigma 1, sigma 2, sigma 3 3 and sigma 1 2 1 3 2 3 are stresses on any other plane, right? And third invariant is given by product of principal stresses, which is nothing but determinant of your stress matrix. So determinant of stress matrix, if you try to write in any other coordinate system other than principal coordinate system, so it will be a large expression. But in principal coordinate system, since only the diagonal elements will be non-zero, it will be product of those diagonal elements, right? Because in a diagonal matrix, determinant is equal to product of diagonal elements. Okay. Now you would have also studied related to octahedral stress components. So what are octahedral stress components? So octahedral stress components are the component of stress on octahedral planes. And what are octahedral planes now? So let me write. So octahedral planes are the faces of octahedron, which have 8 faces. So faces of octahedrons having 8 faces. And whose normal is given by, so normal is given by this form, so which is n vector, that is equal to plus minus 1 by root 3 plus minus. So this is, there are 8 planes, there will be 8 normals, right? So we take combination of these. Let's say you take plus 1 by 3 plus 1 by 3 plus 1 plus 1 by root 3 plus 1 by root 3 plus 1 by root 3. So that will be first normal. Then you take plus 1 by root 3 plus 1 by root 3 minus 1 by root 3. That is second normal. I mean, similarly, you will get 8 combinations. Okay. So and in lectures, so since there are 8 octahedral planes, we see somebody has written in the chat. Yes, somebody has doubt in normal and shear stress. You can ask. Sorry, I missed the message. So you can unmute and ask. Okay, so now you have 8 octahedral planes. So on these planes, you will have normal stresses and shear stresses. So expression for normal and shear stresses on these planes was derived in the class. So let me write the expressions. So normal component of traction, you can say, for octahedral planes. This is given by sigma octahedral, which is nothing but sum of all the 3 principal stresses divided by 3. So that is sum of principal stresses is first invariant divided by 3. So this is also invariant. And okay, so and also you know that obviously these normals are with respect to principal. So these normals are given with respect to principal coordinate axis, right? And here also I'm writing a note. They are octahedral planes. So here, obviously, normal, I have defined a normal. So normal has to be with respect to some coordinate axis. So it's with respect to principal coordinate axis. Okay. So octahedral planes are defined with respect to principal coordinate axis, or the direction of principal stresses will be 3 axes of the coordinate. So octahedral planes are always defined relative to the principal coordinate system. And then you had shear component of traction on octahedral plane. So the above was normal component of traction. Now we have shear component of traction on octahedral plane. So this is given by tau octahedron, which is square root of 2 by 3, and first invariant pair minus price of second invariant. Okay. In this you have shear component of fraction, one of triangle 3. Now you would have also studied related to hydrostatic and deviatoric part of stresses. So let me write that. Hydrostatic and deviatoric parts of straight stress tensor. Right? So this is given by sigma will be equal to 1 by 3 times first invariant of sigma times identity matrix. So this is hydrostatic part, right? And it's invariant with respect to rotation. You can just check. Yeah, because it only contains first invariant, so that is obvious. Plus hydrostatic, I mean the deviatoric part obviously will be uh, the total stress matrix minus this hydrostatic part. So this part is known as deviatoric part. Okay. And you can easily, I mean, it was derived in the lectures also that first invariant of deviatoric part is 0. Was invariant of deviatoric part is 0. So this actually contains, so since first invariant of this deviatoric part is 0, it means there will always exist a set of coordinate system in which all the diagonal elements will be 0, right? Since all the diagonal elements will be 0, there will be no normal stresses, only shear stresses will be present. So we can say that the first part is only normal traction, and this part is state of pure shear. That's why this part actually accounts for this deviatory part accounts for distortion of the body, and there is no volumetric change in the body due to this deviatory part of the stress, whereas this hydrostatic part does not cause any distortion, and only there is volumetric change in the body due to this hydrostatic part of the stress. Now, in the next lecture, you would have studied about deformation gradient tensor. So let me write it down. So it was in lecture 11. So in this lecture, wait a minute. So in this lecture, you would have studied about deformation gradient tensor. right? So this was given by gradient capital F, which is gradient of deformation map, right? Small f, which is given by if you find the gradient of a vector. The small f is a vector function, vector value function. Vector value function, and it is input is vector and output is also vector. So if you just expand it, so it will be del by del x1 f diagonal e1, right? I mean, actually, it should be, you would have learned about the gradient of a vector, definition of gradient of vector. So it is nothing but del by del xi times the vector diagonal ei, right? If you expand it, you will get, so this since I is repeating two times, so it is a repeating indices. So there will be summation over I. I will go from 1 to 3 because x. So we have del f diagonal e1, del f by del x1 diagonal e1 plus del f vector by del x2 diagonal e2 plus del f by del x3 diagonal e3. So you can also write it in terms of, so f can also be written as FIEI. So I'll write F. So this is one notation. Other is, actually, let me write J at the place of I because I will use for different purpose. Okay. So F can be written as FIEI. So I'm just writing, this will be FIEI vector, then del by del xj, and then direct ej. So finally it is del fi by del xj and ei direct ej. So it is a second order tensor. So I will go from 1 to 3. J will also go from 1 to 3. So you can easily uh, find this matrix. So when I will be 1, J will be 1, it will be 1, 1, I is 1, J is 2, so 1, 2. You will even find all the other components. So if I write in summation form, so it will be sigma I, summation will be over I, and summation will be over J. So it will be del small f actually. Del fi or del capital Xj ei direct. So, and in lectures, you would have studied that, let's say this is the reference configuration. So your body has this shape in reference configuration, and let's say after some deformation, the body has reached to this shape, right? So there is a deformation map which is relating these two configurations. And initially, let's say this point has a position vector capital X, and finally this point has been deformed and reached at this place whose position vector is small x. Okay, so you can also write deformation gradient tensors in terms of displacement gradient. So let's write the deformation gradient tensor can be written in terms of displacement gradient. Right. So let's write this. This is deformation gradient, which is identity matrix plus displacement gradient, gradient of displacement vector. So this is known as displacement gradient because it is gradient of displacement vector. and this u is your displacement vector. So let's start with few problems. Let me have some water first. So problem one, first problem. So it says, suppose the state of stress at a point of stress at a point. Yes, the state of stress at a point is as follows. And this is given in XYZ coordinate system, XYZ coordinate system. Okay. So sigma is given by first component is -2, second is 4√3, third is 0, similarly 4√3 is 0, and you have 0, 0, 4. So you can easily identify that this coordinate system is a coordinate system um, with plane normal perpendicular to the third principal direction. So this 4, so there is no shear component present in the third direction. That's why it's a principal direction. So Z is the third principal direction, and now all these stresses are in a plane which is perpendicular to the third principal direction. When this plane is having a plane normal which is perpendicular to the third principal direction. So let me write, right. So this is A. In A, you have to find out the center and radius of corresponding Mohr circle. Okay. And in second part, you have to find out normal stress and shear stress on a plane whose normal makes an angle 15 degree. Anti-clockwise from x-axis. Right. And in the third part, you have to find out what are the values of principal stress components. Okay. So let me find out the center and radius of corresponding Mohr circle. So from this stress matrix, you can easily see that we have sigma xx is equal to -2. We have sigma yy is equal to 6. We have sigma xy is equal to 483. Basically. And we have tau xy. I mean, obviously this is tau xy, not sigma xy. This notation. And we have sigma zz, that is 4, right? So all this information is given to you. Based on this information, you can easily draw more circles. So firstly, let's find out the center of the Mohr circle. So center of the Mohr circle was given by sigma xx plus sigma yy by 2, right? So you can just say that center of Mohr circle, and we are drawing in xy plane. Okay, so this is sigma xx plus sigma y by 2 comma 0, because the shear component will be 0 at the center. And what is the radius of Mohr circle? So if you calculate sigma xx plus sigma y by 0, that will give you value 2 comma 0, right? This will give you 2 comma 0. Now what will be radius of Mohr circle? So radius of Mohr circle, the formula was, you can just imagine. So that was sigma xx minus sigma y by 2 to the whole square plus 2xy to the whole square. It was sigma xx minus sigma y by 2 to the whole square plus 2xy to the whole square and under root of that. Okay. So if you now solve this, so you'll get sigma xx minus sigma yy. So that will be 8. I mean minus 8. So divided by 2 will be minus 4. Square of that will be 16. And 16 plus square of 4 root 3. So 16 plus 48. So how much will you get? You get 64. And square root of that will be 8. You get radius as 8. Okay. So radius of Mohr circle is 8. Now in part B, we have to find out sigma comma tau on a plane whose normal makes an angle 15-degree anti-clockwise from the x-axis. Okay, so let me first draw the Mohr circle. Since I have the radius and center of the Mohr circle, I can draw the Mohr circle now. So just draw it here. This is sigma axis, this is tau axis. And my center of the Mohr circle is here, 2 comma 0, let's say. And so this is center of the Mohr circle. And radius is 8, so this side will go to 10 comma 0, right? And the left hand side will go to 2 minus 8, so minus 6 comma 0. And if I draw a circle passing through these 3 points, so It's finite. Okay. So you have this circle. Now we have to locate where we are. Where is, I mean, we have to locate where we are on the Mohr circle. So on the Mohr circle, since our sigma x is -2 and tau xy is 4√3. So -2 will lie somewhere here, right? So we are here, you can see. So we are somewhere here on the Mohr circle. We are here. And if you draw the radius, so this point is nothing but -2, 4√3. You can easily find out the angle. So what is this angle? This angle will be, so perpendicular is 2 and height base is 4√3. So that will be 1/2. Okay. Actually, this will be 4 only because this length is -2 and this length is 2. So this will be 4 and this is 4√3. So 4 divided by 4√3 will be 1/√3 and tan theta will be 1/√3. So theta will be 60 degrees. Sorry. I'm just saying so this height is 4√3 and this length is 4. So theta, what theta you will get? So theta you will get as 60 degrees. Right? Because this is perpendicular over base, 4√3/4 will be √3. So tan theta will be √3. So theta will be 60 degrees. It means this is your xy plane, right? On the Mohr circle, this denotes your xy plane. Obviously, y will be, so this is sigma xx, sigma y will be somewhere here at this point here. So now, let me see. And your principal plane is making 60 degree. I mean, in the Mohr circle, it is making 60 degree clockwise. So in the physical system, it will make 30 degree anti-clockwise with the xy direction, right? So I mean, I'm saying here actually this is anti-clockwise. So the Mohr circle is making anti-clockwise. So in the real system, it will make clockwise, 30 degree clockwise. Okay. So what do you have to find out? You have to find out sigma comma tau on a plane whose normal makes an angle 15 degree anti-clockwise from x-axis. Let me just draw it here. So here now we have x and y. So here we have this, let's say this denote x, this denote y. And what has been asked? So you have to find sigma comma tau on a plane whose normal makes an angle 50 degree anti-clockwise from x-axis. So this is the physical system, and let's say this is your plane on which you want to find sigma comma tau. This is the orientation of your plane, and this normal of this plane is like this, and it's making an angle of 15 degree, actually 15 degree in anti-clockwise direction from x-axis. So this is your x-axis, and it is making 15 degree from the x-axis in anti-clockwise direction. So in the Mohr circle, it will make 30 degree clockwise. Okay. So this was your, you can say that this was your xy plane in the Mohr circle. So this denote x, and this one will denote y. So anyway, so it will, you have to move 30 degree clockwise. If you move 30 degree clockwise, you get a normal line, right? Because since this angle is 30 degree, right? So this angle is 30 degree. So in total, this 60 and 30 will make 90. So here you have to move 15 degree anti-clockwise. Now here in the Mohr circle, you have to move 30 degree, double of this, and in the opposite direction, that is clockwise. So you're getting this point here. This point is, on this point, your sigma is 2 and your tau is, what is your tau? Tau is radius of this circle. It's 8. Okay. You have got the answer of your second part. This was part A. And part B. So part B, your sigma is 2 and tau is 8. So you can just say that units, whatever the units are. And then you have to, in the third part, you have to find what are the values of principal stress components. Now you can look at this more circle and you can just tell the value of principal stress components. So can you tell? Value is 10 comma minus 6. So it's the maximum and minimum values on the x-axis. The maximum value is 10, minimum value is like minus 6. And obviously the third principal component is this 4 only because here this was the third principal component. So you can say that lambda 1 is 10, lambda 2 is minus 6, and lambda 3. This was given to. Is there any doubt in this question? Okay, so we can move to problem 2. So problem second says the stress tensor at a point is denoted by the following matrix. In Cartesian coordinate system. The matrix is given by this. This is minus 7, 6.30, and this is 6.3, 5 and 0, and this is 0, 0, and 3. Again, you are able to see that third column has here component 0. So the third column denotes the fraction vector on a plane whose normal is perpendicular to the third coordinate. And since there's no shear component, so this denotes that it is the principal plane. And value of principal stress is 3. Okay. So what you have to find out now is, in the first part, you have to draw more circle corresponding to this state for fractions in xy plane. You have to draw more circle in xy plane. Also, you have to find out what are the principal stress components and the direction of principal planes. Find out the principal stress components and directions of principal planes. Also, you have to find what is the maximum shear traction and on what plane does it act. You have to find what is the maximum shear traction and on what plane does it act. Okay. So these things you need to find out. The first part. In the first part, you have to firstly draw a Mohr circle corresponding to this state for tractions in XY plane. Also, you have to find out the principal stress components and directions of principal planes. And you have to find out what is the maximum shear traction and on what plane does it act. So there are three things that you need to find out in part A. Now there is part B, which says, firstly, I mean, in part A, you will be drawing the Mohr circle, and then in part B, you will be using this Mohr circle to answer further questions. So you have to find out part B says using Mohr circle, find out the normal and shear direction. The normal and shear directions on a plane whose normal lies in XY plane and makes an angle 15 degree. From x-axis in clockwise direction. In part A, you will be drawing Mohr circle and then using that Mohr circle, you have to find out the normal and shear tractions on a plane whose normal lies in XY plane. So it's lying in XY plane and it's making 15 degree from x-axis in clockwise direction. So in that case, you'll have to move 30 degree in anti-clockwise direction in Mohr circle from the XY plane. Right. So there's part C. So in this part C, you have to find out the octahedral normal and shear stress components. Just wait a minute. tetrahedral normal and shear stress components. Corresponding to this state of stress. And in the last part, you have to decompose the given stress matrix into hydrostatic and levotoric parts. Okay. So let's start doing this question. It's a lengthy question, so it's going to take a bit of time. So what we will do step by step. It's lengthy but not difficult. Okay. So through this question, we've tried to cover most of the concepts which you have learned during the class. So firstly, you draw more circle corresponding to this state of traction. So how will you do it? Firstly, you can find center and radius. So again, I'm just going to write. Let me just copy this and paste it here. Now you have this matrix. Okay. So you have to draw the more circle. So what is given to you here is your sigma xx, which is -7, sigma yy, so second diagonal component, which is 5, and sigma zz, which is also lambda 3. I mean third principal value, which is 3, right? So now you also have been given with tau xy formula. Tau xy will be 6√3, right? So if you try to find out the center of circle, center of more circle, which is center of more circle. So this will be given by, so this will be sigma xx plus sigma yy by 2. Obviously, comma 0 because their component will be 0. So if you do that, so you get -1, comma 0, right? Similarly, you can find the radius. See, you need not to remember the formula for radius and center because you know that you have sigma xx, sigma yy, center will be average of 2. And for radius, actually, you know that the triangle is formed in the Mohr circle. So the base of the triangle is, if you remember the Mohr circle, the height was tau xy, and the base was the half of the distance between sigma xx and sigma yy. So distance between sigma xx and sigma yy is sigma xx minus sigma yy by 2, and half of that is divided by 2. That is base. The hypotenuse is the radius, which is base square plus hypotenuse square. So that's why you have the formula sigma xx minus sigma yy by 2 to the whole square plus xy square. Right? So you can just put the values. It's very simple. So minus 7 minus 5 will be minus 12, where it will be 6, 6 square will be 36. And if you do 36 times 3, min 2xy square will be 36 times 3. So that will be, I think, 108. So 108 plus 36. So you get 144. Square root that will be 12. Radius will be 12. Okay. Now you have center and radius, you can draw the Mohr circle easily. So let's draw it. So a bigger one. So this is sigma axis, this is tau axis. And you have center at minus 1 comma 0. So this is your, let's say, minus 1 comma 0. So, and you have radius as 12. So here you'll get up to 11 comma 0. And here you will get up to 13 comma minus 13 comma 0, right? Trying to draw the circle very close. I think we have to bring it closer. Firstly, let me draw the circle then. Center maybe. Okay, so this is the Mohr circle. So this, let's say, this is 11 comma 0. This is minus 13 comma 0. This is also you can denote as lambda 2 comma 0, right? And this is lambda 1 comma 0, right? And this is lambda. Okay. This is center. Anyway, so now your sigma x is minus 7 and sigma, I mean, and tau xy is 6 root 3. So minus 7 will lie, let's say, somewhere here, right? So this is your, this is where you are, it's your xy plane. So here you have minus 7 and 6 root 3, right? So this is nothing but this width here is nothing but 6. It has a length of 6 and this has a height of 6 root 3. So this angle theta, so that will be 6 root 3 divided by 3, so that will be 60 degree. So this theta is 60 degree. Okay. So that is an anti-clockwise direction. Anyway, so we have drawn the Mohr circle. So first we have to draw a Mohr circle corresponding to this state of forward direction. Also find out the principal stress component and direction of principal planes. So obviously principal stress components are lambda 1 and lambda 2, right? And direction of principal planes. So uh, we can say that, let me just write. So principal stresses. Principal stresses are given by, we have lambda 1, which is minus 13 comma 0, minus 13, lambda 2, which is 11, and lambda 3 was 4. So in this case, it is 3. You have principal stresses. Now for principal planes. So firstly, for principal planes, you have to find the first principal plane, which is on which the first principal stress is acting. So this is the first principal stress. Okay, so this is inclined at 60 degree with respect to x-axis in more circle. I mean, this is xy plane, so this is corresponding to x, and this, the here somewhere there will be y. So yeah, so this is inclined at 60 degree anti-clockwise. So in physical coordinate system, it will be 30 degree clockwise with respect to x-axis. So we can say that lambda 1 plane, occur at 30 degree clockwise. With respect to x-axis in physical coordinate system. But since we have to always define anti-clockwise, so you can always also say that, let's say this is your physical coordinate system, and this is your x, this is your y, and this was your plane, which was normal was this and vector, and this was making this n vector actually will not be like this, but let's say it's making 30 degree clockwise. So 30 degree clockwise with respect to x-axis means your normal vector will be something like this. Let me just, so say this is, so your normal vector will be something like this, right? So this will be your plane, and this will be your normal vector. This is 30 degree clockwise. Now, if you try to find out anti-clockwise, so obviously this is your normal vector. Anti-clockwise, it will make the same, right? So wait a minute. Just wait a minute. So we always measure angle anti-clockwise only. We do not measure angle clockwise. So because the direction of the thing will be same anyway. So okay. Yeah. So in anti-clockwise, your angle will be 150 degree. So from here you can just see this is 30. So this will be your, so this will be your 150 degree angle. Okay. So actually, your normal vector will be something like this, not pointing in this direction, but rather your plane will be same, but the normal vector will be pointing in this direction. Okay. So we can also say that I think these two systems are same only if even if the normal vector is pointing in this direction or this direction. Of course, this can also be the normal vector, and this can also be the normal vector. Uh, yeah. Okay, so we can also say that it is 150 degree anti-clockwise with respect to x-axis, right? This is fine. Or from here also you can directly measure, if you don't want to get any confusion, you can directly measure angle in anti-clockwise direction only. I'm sorry. In Mohr circle, you have to measure clockwise to get anti-clockwise in physical coordinate system. So in physical coordinate system, since it is always defined anti-clockwise, so you will measure clockwise in Mohr circle. So you start from here and you go up to this principal plane. So this angle will be, so this total angle is 360 degree minus 60 will be 300. So this angle here is with green color. So go here up to principal plane. So this angle is 300 degree. So 300 degree anti-clockwise. So 300 degree clockwise in Mohr circle means half of this anti-clockwise in physical coordinate system. So you will get 150 degree anti-clockwise with respect to x-axis in physical coordinate system. So let me write in physical coordinate system also. So this is the direction of your lambda 1 plane. Now lambda 2 plane. Let's talk about lambda 2 plane. That is second principal stress. So the plane on which second principal stress will be acting. So that plane uh, is in this direction here, second principal stress. So if you measure in clockwise direction, so from you are here at this plane. So if you measure in clockwise direction, so in clockwise direction, this angle will be how much? This angle will be 120 degree. In Mohr circle, your second principal plane is at an angle of 120 degree clockwise with respect to x-axis. So in physical coordinate system, your second principal plane will be at an angle of 60 degree anti-clockwise with respect to x-axis, right? So lambda 2 plane, so that occur at an angle of 60 degree. /60 60 degree anti-clockwise in physical coordinate system with respect to x-axis in physical coordinate system. So since, and we can find the normal vector also. So normal vector will be, since this angle is, so we always, for finding normal vector, we take angle in anti-clockwise direction, so that is 150 degree. So the component of normal vector will be cos alpha sin alpha and 0. 0 because it's lying in xy plane. So this is y. So component of normal vector is cos alpha sin alpha and 0. So cos 150 degree sin 150 degree and 0. What is the value of cos 150 degree? So that is cos 180 minus 30. So yeah, so that will be minus cos 30. So that will be minus root 3 by 2. And sine 180 minus 30 will be sine 30. So that will be 1 by root. And similarly, you can find the normal vector of the second. So here alpha is 60 degree actually. So we'll get cos 60, sin 60 and 0. If you do that, cos 60 is how much? 1 by 2. Sin 60 is root 3 by 2. And this is 0. So now you have to find lambda 3 plane. So lambda 3 plane occurs along z axis, right? Because here in your coordinate system, this axis is already z axis. So you can say that lambda 3 plane occurs along z axis or E3 axis, you can say. E3, E3 plane. So this is obviously normal and plane will be perpendicular to this normal. This is plane normal. Okay, so let's see. So we have found out the principal stress components and direction of principal planes. Now next we have to find out what is the maximum shear traction and on what plane does it act. So actually there will be different maximum shear traction based on whether we are selecting xy plane, xz plane or yz plane. So we have lambda 1, lambda 2 and lambda 3 is lying somewhere here. So lambda 3 is 3. So it says lying somewhere here. So this is lambda 3. Okay. So let's say firstly we find out first maximum shear stress is consistent color. So let's say first maximum shear stress. So that is given by, let's say lambda 1, we take lambda 1, lambda 2 for that. So lambda 1, lambda 2 divided by 2. So since we are taking lambda 1, lambda 2, so this shear stress will lie in the plane, in the xy plane. Sorry. Um, yeah, yeah, in the xy plane only. So because lambda 1, lambda 2 is lying in xy plane. I mean, the plane normal of lambda 1 and lambda 2 will lie in xy plane. So that's why this maximum shear stress will lie in xy plane. So its magnitude will be lambda 1 minus lambda 2 by 2. So lambda 1 is minus 13, lambda 2 is minus 11 divided by 2. If you do that, you will get 12, right? So and let's see in the Mohr circle where it is lying. So lambda 1 minus lambda 2. So we have lambda 1 here, we have lambda 2 here, and obviously it will lie exactly at the center of this circle, right here. So it will lie here. Let me use different colors. So it will lie here, right? So since it is lying here, so it's lying at an angle of 30 degrees. So this angle will be 30 degree clockwise with respect to x-axis. So that's why it will lie in physical coordinate system. It will lie 15 degree anti-clockwise. So we can just say that in physical coordinate system, so max 1 occurs on a plane with plane normal inclined at 15 degree anti-clockwise with respect to x-axis. It means your alpha is 15 degree. So your plane normal 1. So you can just say that. You can name it as 1 because it's corresponding to maximum shear stress 1. So cos alpha sin alpha cos 15 sin 15, and this is 0 because sin lying in xy plane. So cos 15 is and obviously there will be plus minus sign associated with this because it can lie here also. Can lie here also. So this angle may have, this can be 30 and 180 plus 30. So in physical coordinate system it will be 30. I mean it will be 15 and 90 plus 15. So So this will be your angle of maximum. Suppose 90 plus 15 if you distance. Wait a minute. This is one angle 30 degree and the other can be 180 plus 30. So this can be second angle. Okay, so this is given by 180 plus 30. And clockwise, in physical coordinate system, it will be 90 plus 15, right? So if I add and subtract, so first can be cos 15, sin 15, and 0. And the second can be cos 90 plus 15, sin 90 plus 15. To do that, so what will you get? So you can solve this actually. So let me solve this. Cos 15 is 0.966. You can just say first is coming 0.966 and sin t is 0.258 and 0. Okay. So and second one is cos 90 plus 15. So it's coming out to be minus 0.2584. 58. And this is 0.966. So there can be two planes inclined at 90 degree respect to each other. This will be the answers. And this is very fine. This is 30, that is for sure. And this is 180 plus 30. So these two will be at angle of 90, difference of 90. So let's say one plane normal is this, one this. So other plane normal will be like this, right? Let's say this here have x-axis. This will be t. This will be 90 plus 15. So obviously x component will be negative and negative. Anyway, okay. So you can write actually this normal also if you want. Go like this. Yeah, so that's fine. Now you can go to next one from x2. So from x2, let's take lambda 1 and lambda 3. So if we take lambda 1 minus lambda 3 by 2, so it means we are taking in xz plane. Okay. So maximum shear direction in xz plane. So that is given by lambda 1 is minus 13, lambda 3 is minus 3 divided by 2. So we get 8, right? And to get its plane, actually, if you see, so if you see lambda 1, lambda 3 principal plane, okay, so there will be a coordinate system. So one direction is aligned along lambda 1, one is aligned along lambda 3. So you see here that the principal, I mean, the maximum shear stress is at 90° in anti-clockwise direction with lambda 1, okay, in Mohr circle. So it means in physical coordinate system, it will be inclined at 45° in anti-clockwise direction, right, with respect to lambda 1. So with respect to the first principal direction, you can see. So similarly, if we can say here that this term x2 will be inclined at 45° with respect to lambda 1, right? In lambda 1, lambda 3 coordinate plane. Okay, so there will be coordinate axis. There will be a plane normal inclined along lambda 1. So I mean, there will be first principal direction, that is lambda 1, then third principal direction lambda 3. These two vectors will form a plane. In that plane, the maximum shear stress will be inclined at 45° with respect to lambda 1 axis, right? But we have to find the plane normal with respect to xy axis, right? So here we have xy axis. Let's say this is x, this is y, right? In this xy axis, we have this principal direction lambda 1. I'm just referring it, although this is a principal value, I'm just referring it as that lambda 1 is inclined along this direction. So this direction is at what angle with respect to x-axis? So this is, you are able to see here that this first principal direction. So this first principal direction was at an angle of 150° anti-clockwise, right? So yeah, so here actually it is here, not here. So it was somewhere here. So this is your, let's say, so, yeah, so it's here, something else. I'll just tell you what I'm doing. So this was your direction of lambda 1, which was inclined at an angle of 150° anti-clockwise with respect to x-axis in physical coordinate system, because in Mohr circle, this Mohr circle, in this Mohr circle, it is inclined at this red, not this green one, yeah. So this principal plane is inclined at 300° clockwise. So in physical coordinate system, it will be 150° anti-clockwise with respect to x-axis. Now you have this lambda 1 direction, and your lambda 3 direction is perpendicular to this plane. So this is your lambda 3. This is perpendicular to x and y. Okay. So this is in, you can say this is in xy plane, and this is perpendicular to xy plane. Right. Now what you have to do is you have to form a set of planes, including lambda 1 and lambda 3. So you see here that, what should I explain to you? Just wait. So let's say you have this. This is your yeah. So let's say this is your x-axis. Let me restart. So let's say this is your x-axis and this is your y-axis. You can imagine this is your x-axis and this is your y-axis. These two sides are perpendicular, and this is your z-axis. So this pen denotes your lambda 3, right? And your lambda 1 is lying in this plane only, this yellow plate, on this yellow plate only. So this is your lambda 1, but this is inclined at, so this is x-axis. So this is inclined at 150°, so it will be somewhere here. Let's say it will be somewhere like this in this plane only. So include, now you have to form a plane which is passing through both this is lambda 3, and let's say lambda 1 is in this plane. Let's say it is inclined like this. here. How do I show? Okay, so let me show it like this. Okay, now I think. Okay, so yeah, so your lambda 3 is somewhere in this plane only. So you have to form a plane passing through lambda 1 and lambda 3. So it will be something like this. Okay. So this plane, in this plane, your Tom X is lying, and it is making 45-degree with respect to lambda 1. So lambda 1 is lying here and it is making 45-degree respect to lambda 1. So it means it will be the resultant will be uh, so what will be the resultant vector in XYZ coordinate? So you can see this is one vector and this is another vector. So this is one vector lambda 3, which is E3, and this is another vector. We know what is this vector in terms of in XY coordinate. This vector is given by lambda 1 we have derived. So yeah, so it is minus root 3 by 2 E1 cap, 1 by 2 E2 cap, and 0 E3 cap. Okay. And we want a resultant now in XYZ coordinate system, which is at 45-degree with respect to this n vector. Okay. So what you will get? So what I'm saying now is you will get some vector. So let's say you have a vector A. So when you have vector A and vector B, and you want to get a resultant vector inclined at 45-degree with respect to these two vectors, so that will be A plus B, right? So A plus B will be some resultant vector, and let me just show you. Let's say this is A, this is B. We'll form a rectangle now. So this is the diagonal. Diagonal will make 45-degree angle with respect to A or B, both of them. So this diagonal vector will be resultant vector, which is given by A vector plus B vector. But it will not be a normal vector. I mean, it will not be a unit vector, but we want to get unit vector. A is also a unit vector, B is also a unit vector because A was n cap, which was the direction of lambda 1, and B is in our case is E3, which is so both are unit vectors. So to get the unit vectors, we just divide by magnitude of A vector square plus B vector square. Okay. If you divide by the magnitude of this vector, you get. Sorry, I think. Yeah. So you just divide by the magnitude of A plus B. Finally, we'll get this. Okay. So now what will be our vector? We can just say. So I can just name it as N2, N2. So that will be combination of um, N vector plus N vector, which was derived earlier. So that was um, minus root 3 by 2, 1 by 2, and 0 plus this vector 0, 0, 1, E3. Okay. So what will you get? And divide by the magnitude of these two. I mean, combination of these two. So magnitude of this will be root 3 by 2 plus 0 will be minus root 3 by 2. So just to do the square of components. So this will be 3 by 4 plus 1 by 4 plus 1, right? So you can just say what you will get. You will get 1 plus 1 root 2. So finally what you will get is 1 by root 2 times this vector minus root 3 by 2, 1 by 2, 0 plus second vector 0, 0, 1, right? So if you solve this, you will get 1 by 2, root 3 by 2, and 1. And this is 1 by root 2. So this is your N2 vector, and this is in XYZ coordinate system, or you can say EX. Yeah, so let's say xy. So we have found the normal vector to the plane on which traction is maximum, on which the shear component of traction is maximum in lambda 1, lambda 3 planes. Okay. So, but we have found the plane normal with respect to xy z axis, not lambda 1, lambda 3 axis. Because in lambda 1, lambda 3 axis, actually, okay, we'll have to find with respect to x axis only, xyz axis only. Okay. So, because with respect to lambda 1, it was inclined at one, it was inclined at an angle of 45 degree in anti-clockwise direction. Okay. So, it will be somewhere here, anti-clockwise 45. And this is in this plane, lambda 1, lambda 3 plane. Lambda 3 is out of plane vector, out of plane to the xy plane. Okay, so let me quickly go to the next part. Yeah, so you can at last you can take Tomex 3. So Tomex 3. So that will be combination of lambda 2 and lambda 3. So that will be UML of lambda 2 minus lambda 3 by 2. So that will be lambda 2 is 11, lambda 3 is 3. So that will be 4. You get 4, and you can get n3 plane. So that will be inclined at 45 degree to the lambda 2 axis, right? So that will be 1 by root 2 of direction of lambda 2 and lambda 3. So direction of lambda 2 was 1 by 2, root 3 by 2, and 0 plus 0, 0, 1. That will be 1 by root 2 of 1 by 2, 3 by 2, and 0. So that's how we have got n3. Now coming to the next part. So next part says using Mohr circle, you have to find out the normal and shear traction on a plane whose normal lies in xy plane and makes an angle 15 degree from x-axis in clockwise direction. So whose normal is lying in xy plane and is making 15 degree from x-axis in clockwise direction. So in Mohr circle, it will make 30 degree from x-axis in anti-clockwise direction. So 30 degree from x-axis in anti-clockwise direction. So you will reach here, right? Oh, sorry. Yeah, this way. You have to move this way. Opposite way. Okay. So 30 degree from x-axis in anti-clockwise direction. So you will reach here. So somewhere, just wait a minute. Somewhere here you will reach, right? Let's say this angle is 30 degree. And now here you have to find sigma comma tau, which is very easy because now you have a 30 degree angle. So how will you find it? You know the value of radius, right? So radius is 8, sorry, 12. Okay. So you know the value of radius. So this component will be a normal component, which is, so this angle will also be 30. So r cos 30 will be, so you can just say that sigma will be r cos 30 and sigma comma tau. So we can just say that sigma will be r cos 30 and tau will be r sin 30. So part B. Actually, it's not simple. So r cos 30 will be this distance, right? And you have to add -1 also to it to get this coordinate. And obviously it will be minus only, minus r cos 30 -1. So let me just write it. So finally, and then this will be r sine 30. So if you solve this, so you'll get this will be minus 11.39, and this will be 6. And coming on to the third part says find out the octahedral normal and shear components corresponding to this state of stress. And fourth, you have to decompose the given stress matrix into hydrostatic and deviatoric parts. So octahedral, you don't directly have the expression, you just put the values. So second question, third part. So octahedral normal stress. So that is given by sigma octahedral. So that will be 1 by 3 I1. That will be 1 by 3 sigma 1 1 plus sigma 2 2 plus sigma 3 3. And that is given by, so obviously it can be also be equal to lambda 1 plus lambda 2 plus lambda 3. So lambda 1 is minus 7 plus 5 plus 3. Actually, you can do sigma 1 1, sigma 2 to sigma 3 3 also. So this is here given to you minus 7, 5, and 3. So from here, you can also take lambda 1, lambda 2, lambda 3, whatever you want. Summation will be same. So do that, you will get 1 by 3. And similarly, you can calculate tau octahedral. So that expression is, you know, that you have 1 by 3, and this is twice of I1 square minus 6 of I2. You already have I1. For I2, you need sigma 1 1, sigma 2 2. So here I'm referring not to principal values, but to the stress matrix that is being given in the question. Plus sigma 2 2, sigma 3 3, plus sigma 3 3, sigma 1 1, minus sigma 1 2 square, minus sigma 1 3 square, minus sigma 2 3 square. Right. So we put all the values. Actually, it is tau. You can just from sigma. Summation tau 1 to tau 3 tau. Just put the values, you will get final answer will be just writing the answer. So it should come 9.977. And finally, at the last, you have to find the hydrostatic state of stress, part D. So you have to find hydrostatic part of given stress matrix. So if you remember, hydrostatic part was given by sigma hydrostatic, you can write. So that was nothing but 1 by 3 I1 times identity matrix. I1 we have recently find out. So I1 is nothing but 3 only. So wait a minute. So I1 is 1. So 5 plus 3 minus 7. So that is 1. So I1 is 1. So it boils down to 1 by 3 times I. So 1 by 3 times I is 1 by 3, 0, 0. Okay. And deviatoric part. So if we try to find out deviatoric part of the given stress matrix, so we can just denote it as sigma T. So that was nothing but total stress minus the hydrostatic part, right? So you already know what is the total stress that is given to you. So there is minus 7, 6 root 3, 5, I mean 6 root 3, 0, 5, 0, 0, 0, 0, 3. and then you subtract the hydrostatic part, which is 1 by root 3 0 0 0, 1 by root 3 0 0 0. Yeah, 1 by 3. So finally, minus 7 minus 1 by 3, so we get minus 22 by 3. And 6 root 3 minus 0, 6 root 3, and this will be 0. This will be 6 root 3. Only diagonal components will change. 5 minus 1 by 3 is 14 by 3. And 3 minus 1 by 3 is 8 by 3. This is what we have got. So we will stop here for today. And in this class, we have only gone into depth of Mohr circle. So in the next class, we'll start with some problems on strains and strain tensor. Okay. And different definitions of strain. So thank you for joining, and we will meet in the next week. Thank you.
Thank you, sir.
Yes. If you have any questions, you can ask me. So
Sir, point number C, I could not understand.
point number C.
Yes, sir.
So octahedral normal stress, actually, you would have learned about this formula in while watching the lectures, right? So it is given by 1 by 3 times the first invariant of stress. And first invariant, what is first invariant? So first invariant is summation of the diagonal components, right? So this is sigma 1 1, sigma 2 2, sigma 3 3. So sigma 1 1 is given to you, which is minus 7. You see this matrix, stress matrix here, minus 7 5 3. So sigma 1 1 plus sigma 2 2 plus sigma 3 3. So if you add all of these, you will get first invariant, and this will be 1. You can also calculate first invariant from uh, because this is invariant with respect to rotation. So even if you rotate this stress matrix, stress tensor, so that it aligns along the principal direction, first invariant is not going to change, and in principal direction, first invariant is going to be lambda 1, because diagonal components will be lambda 1, lambda 2, and lambda 3. So it will be lambda 1 plus lambda 2 plus lambda 3. So lambda 1 plus lambda 2 is minus 2, and lambda 3 is 3. So minus 2 plus 3 is again 1. So that will also be same. So this is your sigma octahedral, and then tau octahedral. You need to find out. So that is dependent on first and second invariant. So this is the formula. The second invariant is calculated like this. So firstly, you have to do pairwise product of normal stresses. Then you have to subtract the square of the CS stresses. Okay. So
Yes, sir, I got it.
yeah. So what is your doubt?
That one I was not following. That did not follow. Na, that's why I asked you, sir.
Okay. Now have you
The
understood?
sigma. Yes, sir.
Okay.
Thank
Is
you
there
so
any
much.
other question?
No, sir.
So have you understood this part? I think this was the this part. This thing was somewhat difficult to understand. Have you understood this? How we have arrived at this N2 vector?
Yes, sir, I got it.
Okay. Okay, then we'll stop here for today. We'll meet in the next class. Thank you.